You clicked because you want to know what's out there, but I should warn you, these aren't the kinds of facts that bring comfort. In 2025 alone, we've seen reports of a gamma ray burst longer and stronger than anything on record, along with new dark energy measurements that only deepen our confusion about the universe itself. Scientists continue to uncover black holes of unimaginable scale, silent voids stretching across millions of light years, and threats that orbit far closer to home than most people realize. And the most unsettling part is how little of existence we truly understand. The unknown universe, 96.5% mystery. When scientists measure the universe at its largest scales, they find something astonishing. About 95% of it is made of substances we cannot see or define. Roughly 70% is dark energy, an unknown force driving the acceleration of cosmic expansion, and about 25 to 27% is dark matter, the invisible mass that holds galaxies together through gravity. That leaves less than 5%, ordinary matter, for everything that makes up stars, planets, and life itself. This breakdown makes our familiar universe feel like a thin surface layer. All the galaxies visible through telescopes are only the faint residue of a much larger and stranger composition. And yet, without both dark matter and dark energy, even that slice of reality wouldn't hold together. Galaxies would scatter apart, cosmic structures would dissolve, and expansion would not unfold in the way it does. What unsettles researchers is not only how little of this unseen universe we've defined, but how the newest measurements resist neat explanations. In 2025, the Dark Energy Spectroscopic Instrument, DESI, released results based on the most extensive 3D map of the cosmos ever created. Instead of confirming existing models, the data hint that dark energy might not be constant. Its influence could be changing with time, which would mean the standard framework of cosmology, the model on which decades of predictions rest, is incomplete. Imagine trying to describe the whole ocean while only seeing the foam on its surface. Our understanding of reality works much the same way. Theories of everything are built upon the small fraction of matter we actually recognize. The DESI findings underscore how fragile this foundation is, reminding us that even the forces that dominate the universe may shift in ways we do not yet understand. The implication is not only scientific but existential. If the force driving cosmic acceleration can evolve, then the universe's far future may look profoundly different than what textbooks describe. Expansion could slow, stop, or collapse altogether, reshaping every projection people once considered certain. And while questions about dark matter and dark energy sit at the center of cosmology, the universe reminds us of its dangers in more immediate ways, events that unleash staggering amounts of energy without warning. Gamma ray bursts, stronger than ever recorded. Gamma ray bursts in 2025 show just how extreme these cosmic explosions can be. They are known as the most energetic outbursts in the universe, events that momentarily outshine entire galaxies and release energy on scales far beyond supernovae. Unlike gradual stellar deaths, these eruptions ignite suddenly, sometimes lasting only seconds, and then vanish, leaving an afterglow across X-ray, infrared, or radio signals. Scientists are intensely focused on them because, despite decades of study, their origins remain uncertain. Two recent discoveries brought this mystery into sharper focus. The first is GRB 221009A, often called the Boat, short for the brightest of all time. This event was so luminous that it overwhelmed detectors, pushing past the upper limits of what astronomers had ever recorded. Observed in 2022 and studied closely in 2024 with the LSD-1 telescope, astronomers measured an unprecedented excess of extremely high-energy gamma rays. The data suggested a structured jet, an ultra-fast, narrow beam surrounded by a slower, wider outflow, likely responsible for its extraordinary brightness. Then, in 2025, came GRB 250,702. This burst broke every rule by lasting nearly a full day and emitting repeat signals over several hours. Typical bursts are over in seconds. Yet here, multiple peaks were observed by instruments like NASA's Fermi Gamma Ray Space Telescope and the Einstein probe. The European Southern Observatory's Very Large Telescope later traced the source to a galaxy far beyond our own, a discovery implying extraordinary power given its distance. The repeating nature of the event defies current models. GRBs are expected to be singular, catastrophic events, not recurring blasts. Both bursts highlight the peril of what might happen if such a phenomenon occurred nearby and was directed at Earth. A gamma ray jet could flood the atmosphere with ionizing radiation, breaking apart molecules and destroying ozone protection. The result would be drastic ultraviolet exposure at the surface, causing biospheric collapse and mass extinctions. While the alignment required for such devastation is rare, the possibility underscores how vulnerable our planet remains. Which of these new extremes, the ultra-bright boat or the day-long repeater, poses the greater mystery, and what do they reveal about stellar deaths and black holes? Scientists are only beginning to explore these questions, but while explosions dominate the headlines, another silence in the universe feels just as unsettling, measured not in seconds but across trillions of potential worlds. Trillions of worlds, yet silence. As of 2025, NASA's confirmed exoplanet catalog reached roughly 6,000. Each world represents a different type of environment. Some are scorched gas giants brushing against their stars. Others are rocky and small like Earth. Beyond these confirmed discoveries, astronomers estimate that billions of planets exist within the Milky Way alone, and many orbit in zones where liquid water could be stable. Statistically, these conditions raise expectations for life. Yet despite vast opportunities, no confirmed signal of biology or technology has ever been detected. That absence feels sharper with every milestone. The expanding exoplanet census has only increased the tension within the Fermi paradox, the question of why we detect no evidence of extraterrestrial life in a galaxy that should allow it on a grand scale. The math favors crowded skies, yet results continue to be blank. Instruments like the James Webb Space Telescope are now stepping beyond simple detection into characterization, probing the chemistry of exoplanet atmospheres for biosignatures such as oxygen, methane, or other disequilibria that could point to microbes or industry. But so far, every candidate world has revealed nothing conclusive. The silence has held. Scientists see two broad possibilities. One is that intelligent civilizations are far rarer than expected. Earth could be among a vanishingly small set of worlds where complexity arose. The other is that civilizations might be fragile, reaching a threshold of technology before collapsing, too quickly for us to detect their presence. Both interpretations deepen the problem rather than resolve it, because the statistical weight of trillions of planets throughout the universe keeps suggesting that life should be common. The psychological impact is real, though it rarely makes the data tables. Each new exoplanet represents another chance to overturn the silence, and each year without a detection makes that stillness harder to ignore. A universe so abundant in worlds should display some trace of companions, yet none appears. For scientists, this is not just a mathematical puzzle, but a reminder of how precarious our assumptions are about life's persistence beyond Earth. And while the silence across distant stars raises questions about cosmic neighbors, a more immediate concern lingers much closer to home: objects in our own solar system that could threaten Earth without warning. Newly spotted hazards near Earth. A threat to life on Earth does not need to come from distant galaxies. It could arrive in the form of a rock already moving within our solar system. Collisions have marked Earth's history before, wiping out species and reshaping environments. And the unsettling reality is that many potentially hazardous objects still escape our notice. What makes current discoveries significant is how much better our instruments have become at revealing what was invisible only a short time ago. In 2025, the Vera C. Rubin Observatory released its first test images, identifying more than 2,000 new asteroids, including 7 near-Earth objects, in a single dataset. This achievement instantly illustrated how incomplete our previous monitoring had been. Large objects capable of catastrophic damage were passing through our neighborhood undetected until very recently. The fact that Rubin could spot so many with its first look is both reassuring and sobering. Reassuring because our tools are improving, sobering because it confirms the scale of what we were missing. Complementing ground-based surveys, NASA's NEOWISE mission continues to map asteroids in infrared, revealing objects too dim or sunlit to track by optical telescopes. Together, these technologies are closing gaps in planetary defense, providing earlier warnings and more precise orbit predictions. But the more successful they become at cataloging asteroids, the clearer it is that Earth has been living under a constant crossfire, spared only by chance alignments of orbital paths. The danger does not depend solely on massive planet-scale objects. The 20-meter asteroid that detonated over Chelyabinsk in 2013 injured over 1,000 people despite never reaching the ground. A rock several hundred meters wide could level an entire region, and larger impactors would shift the course of the global climate. These are not abstract possibilities. Asteroids skim past Earth on a regular basis, most without drawing public attention. Each close pass reminds scientists of how little buffer time humanity might have if a true impactor were discovered on a direct course. Yet preparation has advanced beyond detection alone. NASA's DART mission in 2022 demonstrated that a spacecraft could successfully alter the orbit of an asteroid, and the upcoming Hera mission from ESA will study the impact site in detail. China has announced its own plans to test a kinetic deflection mission, signaling that planetary defense is becoming a global endeavor rather than a single-nation project. The message behind all these efforts is not one of hopelessness, but of fragile opportunity. With wider surveys like Rubin and upcoming missions such as NEO Surveyor, blind spots are shrinking. Our defense rests on whether we detect threats in time to act. And time is a theme that extends beyond planetary defense. While we work to guard Earth against sudden extinction, one of humanity's farthest machines continues on its own path, heading steadily away from us into a future that will last billions of years beyond our species. Voyager 1, humanity's loneliest messenger. Voyager 1, launched in 1977, is now humanity's most distant creation, pressing onward through interstellar space. In 2025, it sits more than 24 billion kilometers from Earth, moving at over 60,000 kilometers per hour. Its faint radio signal, requiring more than 22 hours to cross the void, still reaches NASA's deep space network, though weaker with every year. Out beyond the heliosphere, our sun is reduced to just another point of light, and no other human-made object has entered this realm. Scientists today describe Voyager 1 less as an active mission and more as a fading transmission. Its power source has diminished year by year, forcing engineers to shut down instruments to conserve energy. A handful remain operational, sending back fragments of data about charged particles, cosmic rays, and magnetic fields in interstellar space. But with its generator expected to fail within the next few years, every update now could be its last. The silence surrounding it looms closer each day. This endurance has made Voyager 1 more than a spacecraft. It is a fragile outpost of humanity at the edge of the unknown. On board is the Golden Record, a copper disc coated in gold, packed with sounds of Earth, images of its landscapes, and greetings in dozens of languages. It was never meant as a beacon, but as a time capsule, a small attempt to preserve the fact that humanity once existed. Out here in a void far beyond communication, the record drifts as an artifact rather than a message, surrounded by nothing but silence. The frailty of Voyager's systems contrasts with the inevitability of its journey. Long after its transmitter fails, the probe will continue its path through the Milky Way as a silent relic. Whether it is ever seen again does not matter. What matters is the reminder that, for a brief moment, human beings reached far enough to send a trace of themselves across the stars. Voyager 1 embodies both our persistence and our impermanence, an object built to outlast its makers, yet destined to wander without response. Its distance and isolation reveal something larger. Space is not only vast, it is endlessly stretching. And that truth, written into the structure of the cosmos itself, may be harder to grasp than any spacecraft's lonely path. The universe's endless expansion. The universe itself is not static, it is expanding. This does not mean galaxies are moving into some waiting void. Instead, the very fabric of space is stretching, and as it grows, the distances between unbound galaxies increase. Beyond a certain threshold, those galaxies recede so quickly that their light can never reach us, placing them permanently out of contact. Expansion is not motion through a container, but change in the background itself, unfolding everywhere at once. Over time, this process guarantees isolation. Galaxies we can see today drift farther away, and eventually their light will fade beyond detection. The night sky would no longer show the crowded web of clusters we now observe, but only the faint glow of our own local group. Every location in this expansion looks like the center, yet none actually are. That strangeness is part of why cosmologists emphasize how differently the universe behaves on large scales compared to anything humans can experience. For people used to boundaries and objects with edges, the concept is unsettling. Expansion has no outside to grow into. It is not spilling across a border. It is simply increasing everywhere. That means there is no vantage point from which to watch the universe expand around us, because we are inside it, carried along with the same distortion of space. The human mind resists the idea of limitless growth without a frame, but that is the reality the data confirm. The fate of this expansion depends heavily on the role of dark energy. For years, the standard model suggested a constant, unchanging push driving acceleration. But Dacey's 2025 results provided the strongest hint yet that dark energy might change over time, complicating predictions. If it weakens, expansion could slow or even reverse. If it strengthens, galaxies will be pulled apart at an even faster rate, making isolation more complete. The uncertainty surrounding this prospect leaves physicists questioning whether existing theories are adequate to describe the universe's future at all. Debates over the Hubble constant reinforce that unease. Different tools for measuring the rate yield conflicting answers, with early universe data suggesting one pace and local observations another. No clear reconciliation has been found, and until it is, cosmology remains without a settled framework for the most basic parameter defining the size and shape of time itself. All of this points to a universe with directions we cannot follow and futures we cannot yet map. And within such immensity, the position of Earth itself begins to shrink in meaning, becoming smaller than most people are ready to imagine. Humanity's cosmic insignificance. Humanity's cosmic insignificance becomes immediately clear when set against the universe's scale. All of recorded history, from the earliest civilizations to today, is less than a blink compared to billions of years that have already passed. Civilizations rise, empires collapse, and technologies advance, yet these spans add up to less than a breath on the timeline of the cosmos. Even the entire existence of our species would barely register on a cosmic calendar, stretching across 13.8 billion years. In practical terms, our presence changes nothing about how the universe behaves. Stars will continue burning, galaxies will continue forming and dispersing, and black holes will consume matter at the edges of known space, no matter what happens on Earth. Catastrophic events like gamma-ray bursts or collisions between massive objects occur with or without witnesses. If Earth were erased tomorrow, the expansion of the universe would continue exactly as before. In cosmic terms, our actions don't alter large-scale cosmic evolution, which unfolds on timescales far beyond human history. This perspective may feel humbling, even unsettling, but it does not erase the importance of what existence feels like to those living it. Our sense of time, memory, and continuity creates the framework through which we measure meaning. Yet even that foundation is less stable than it seems. What feels uniform and reliable turns out, under closer observation, to operate very differently depending on where you are. And it is here, in the flow of time itself, that the universe reveals another distortion, just as disquieting as our smallness in space. Time itself is distorted. Time itself is not the steady, universal rhythm we imagine. Instead, it bends under gravity, warps with mass, and flows differently depending on where you are. The unsettling reality is that there is no single, synchronized clock governing the universe. What feels like a constant heartbeat of existence is instead relative, tied to the strength of gravitational fields and the positions of observers. Einstein's theory of general relativity first revealed this strange truth. The stronger the pull of gravity around you, the more slowly time moves compared to regions where gravity is weaker. The effect is subtle on Earth, but it is real. Atomic clocks placed at different altitudes measure different ticks, with higher clocks running slightly faster than clocks kept closer to the ground. Engineers who designed the global positioning system had to factor in these differences. Every GPS satellite carries clocks that drift compared to those on Earth, and without corrections for both gravity and velocity, the system would rapidly lose accuracy. Every map we rely on today only works because hidden relativistic adjustments keep the world aligned. Those tiny differences become dramatic near cosmic extremes. Around massive black holes, gravity stretches time so violently that what feels like minutes to someone close to the edge could look like millions of years passing to an observer farther away. In these extreme regimes, reality divides. Two perspectives on time exist simultaneously, both correct, yet completely incompatible. For one traveler, moments pass normally. For the other, time appears to be almost frozen. Nothing about that is intuitive, and yet the physics leave no room for doubt. This means time is not a single, shared current moving equally for all things. It is fractured, distorted, and stretched, depending on where matter gathers and how it bends space around it. We live as though every second is the same for everyone, but relativity proves otherwise. The passage of time is local, not universal, and each place in the cosmos measures it differently. That recognition shifts how we think not only about physics, but about existence itself. If even time is relative, then many of the assumptions we hold about order and uniformity are illusions. And once those illusions fall away, we are left with deeper questions. Questions about our place in the universe and whether, in the silent expanse, our species is truly alone. Alone or not alone, both terrifying. The most unsettling dilemma of all is the question of other intelligence. The vast surveys, the endless signal searches, and decades of quiet have left us with only a harsher paradox. The universe is filled with opportunities for life, and yet the response to our presence is silence. NASA's catalog passed 6,000 confirmed exoplanets in 2025, with billions more predicted just in the Milky Way. Every discovery raises the odds that life could emerge elsewhere, but every year without contact deepens the mystery. This silence creates two distinct outcomes, and each is disturbing in its own way. If we are alone, then all consciousness in the universe begins and ends with us. If we are not alone, then civilizations older and more advanced may already exist, and we have no idea how they might view us. Both possibilities alter how we think about survival. The first implies that if humanity were to vanish, the universe would have no observing mind left to wonder at its structure. The second implies that if minds beyond ours exist, they may not grant us significance. To them, our presence could be as minor as an insect on a branch, visible but irrelevant. In either scenario, the future feels heavy with risk. The tension comes from the numbers. 6,000 known worlds are only the beginning, each one a reminder that Earth is not alone in conditions, only in evidence. For scientists, this contrast forces sharper questions. Do civilizations inevitably collapse before mastering interstellar contact, or are they deliberately avoiding us? The explanations shift between bleak inevitability and cautious restraint, but none provide comfort. Philosophers in 2025 argue that this paradox mirrors something deeper about mortality. Humanity craves connection because the alternative, solitude on a cosmic scale, feels unbearable. Yet the opposite, discovery of an intelligence far older, may be worse, because it strips away the illusion that we would ever be in control of the encounter. Both outcomes challenge our sense of meaning in ways daily life rarely forces us to consider. And behind both possibilities is the persistent backdrop of space itself, not only filled with countless stars and chances for life, but marked by vast regions where almost nothing exists at all. These regions embody absence in a way that defies our usual sense of scale, places defined not by what they contain, but by what they lack. Voids of nothingness. Cosmic voids confront us with another unsettling truth about structure on the largest scales. These vast regions, some hundreds of millions of light-years across, are defined not by what they hold, but by how little they contain. They form as part of the cosmic web itself, where matter clumps along filaments of galaxies, leaving behind enormous depressions that remain almost empty. Unlike galaxy clusters that glow with starlight, these spaces are strikingly barren, containing only a handful of galaxies where thousands would otherwise be expected. The Boots Void, one of the best known, stretches nearly 330 million light-years, a reminder of just how widespread and immense these low-density regions can be. For an observer, the idea is difficult to process. In a galaxy-rich universe, we tend to think of emptiness as relative, a bit of blank space amid stars. But a true cosmic void is emptiness on a scale that resists imagination. Removed from familiar reference points, there would be nothing recognizable, no nearby stars to orient against, and scarcely any light at all. Scientists simulate what such a viewpoint might look like: a featureless expanse, directionless and black, where turning in circles would reveal the same horizonless darkness again and again. These voids are not static features frozen in place. They shift over cosmological timescales as matter continues to flow toward filaments and clusters, deepening the contrast between dense and sparse zones. Studying them is crucial for understanding the distribution of matter and the way galaxies evolve. They serve as natural laboratories for testing dark matter models, structure formation, and even the effects of dark energy shaping the large-scale universe. In a sense, cosmic voids are not just absences, but active participants in how the universe unfolds, markers of the unevenness that defines its structure. The immensity of a cosmic void is easy to underestimate. Placing an object like the Milky Way at its center would entirely change how the universe looks. The familiar band of neighboring galaxies that fills our telescopes would vanish from view. Instead of a sky filled with possibilities, all that would remain would be blackness stretching beyond any imaginable reach. Voids remind us that most of the universe is not crowded with light, but dominated by profound scarcity. And that sense of absence becomes even more striking when applied to something closer to home: the stars that seem so enduring in our night sky, yet are equally temporary. The dimming of the stars. The dimming of the stars is one of the most striking consequences of the universe's expansion. The light from distant galaxies is stretched as space itself grows, a process known as redshift. Over billions of years, this shift pushes their glow further into the infrared and eventually beyond anything our eyes, or even our most advanced telescopes, can detect. What we see tonight in the form of bright, scattered galaxies is temporary. Their light is fading, and the future sky will progressively lose these distant markers until they vanish altogether. This change will extend to the stars themselves. The constellations we recognize are fragile arrangements, their shapes held together only by perspective from Earth. Expansion, stellar drift, and the life cycles of stars ensure that these patterns will scatter and disappear across time. In the far future, the night sky that guided humanity for generations will dissolve into emptiness, leaving no familiar features behind. The vision of a silent, black horizon will replace it, one more profound than any darkness we know today. For anyone alive now, the view of a star-filled sky is a rare gift localized to this moment in cosmic history. Billions of years from now, an intelligent observer could exist in the Milky Way and still see nothing but their immediate galactic neighbors. To them, the idea of a richly populated universe full of visible galaxies would be pure speculation, a truth erased by time and distance. The stars above us belong not to eternity, but to a temporary age already fading as expansion continues to accelerate. The emotional weight of this realization is heavy. The night sky has always been one of humanity's most reliable sources of meaning and orientation. To know that it is transient, that its beauty is a fleeting snapshot we just happen to inhabit, reframes how fragile our position really is. The sky is not permanent. It is a window destined to close. And when it does, the dark silence will not only be visual but absolute, cutting us off from contact in ways deeper than light. That silence goes beyond what we can see. In the vacuum of space, even the stars that burn so fiercely remain inaudible, their immense power unfolding in total quiet. If space carried sound, imagine for a moment that space carried sound the way the air around us does. The bursts of energy inside every star, the turbulence of plasma churning beneath their surfaces, and the nuclear reactions driving their cores would unleash a constant roar. The sun alone would overwhelm human hearing, vibrating with such intensity that its output would make silence on Earth impossible. Multiply that by every star in every galaxy, and the night sky would not be filled with quiet points of light, but with a deafening wall of endless noise. That vision belongs only to imagination mode. In reality, space remains silent because it carries no medium to transmit sound. On Earth, sound is the vibration of particles in air, water, or solid material, each one pushing against the next in waves. But space is a near-perfect vacuum. It lacks atoms dense enough to pass along those vibrations. No matter how powerful the internal activity of stars, no ear could ever hear it propagate across the emptiness. The silence we experience is not simply a consequence of distance, but of physics itself. Still, the sun does generate what might be called acoustic-like waves, even though they do not leave it. Deep inside, nuclear fusion drives oscillations that ripple through its plasma, constantly resonating and shifting its surface. Scientists measure these oscillations using a technique called helioseismology, which lets them map the sun's internal structure in the same way earthquakes reveal layers within Earth. Sometimes these oscillations are even turned into sound through sonification, converting the collected data into audible tones. What we hear is not the actual roar of the sun, but a transformed signal that captures its rhythms in a way humans can understand. These studies show how dynamic stars really are. Each one, from small dwarfs to giants far larger than our sun, pulses with turbulence and hidden movement. If a medium like air filled interstellar space, the combined sound of countless oscillations would have defined existence itself as a violent and ceaseless tide of noise. What we call silence is in fact protection, allowing life on Earth to exist without being erased by the very stars that sustain it. But while stars themselves pose this theoretical thought, other cosmic objects are not just active, they are overwhelming by their very scale. Among them are black holes, colossal entities whose size and influence reduce our sun to near insignificance. Black holes, the monstrous scale. Black holes on the largest scales are unlike anything else in the universe, and among them, TON 618 is one of the most striking. This object sits at the center of a distant quasar, drawing in gas and dust at such an extraordinary rate that it radiates across the electromagnetic spectrum, outshining entire galaxies. While many people know black holes as objects that swallow stars or crush planets, TON 618 shows that this process can be magnified to a level so immense it challenges our ability to imagine it. Instead of measuring against stars or planets, astronomers compare black holes of this class to whole galaxies. TON 618 has a mass estimated at about 40 billion suns. To put this in context, our own star already outweighs every planet, asteroid, or comet in the solar system combined. Multiply that by tens of billions, and you begin to approach the crushing weight concentrated in the singularity of this one black hole. Such mass does not merely pull objects inward, it alters the very structure of space and time itself. The scale of an event horizon like TON 618's is enormous, a boundary where not even light can escape. Around it, space-time is pulled into curves so steep that all normal trajectories end inward. The accretion disk, where matter spirals toward destruction, produces radiation so powerful that it can be detected across billions of light years. This is why quasars, the luminous beacons fed by supermassive black holes, serve as cosmic markers of activity in the early universe. They are not just evidence of collapse, but of transformation, tapping into processes that release more energy than countless stars combined. For scientists, TON 618 and other supermassive black holes provide a natural laboratory for testing the most extreme predictions of general relativity. Light bends violently as it passes near their edges, and time itself slows for anything caught within their gravitational fields. Observing these phenomena allows physicists to study matter and energy under conditions impossible to reproduce anywhere else. Each measurement adds to our understanding of how galaxies have evolved and how such central engines may have shaped the cosmos throughout its history. The existence of black holes at this scale underscores the fragility of ordinary systems like our own. While galaxy-spanning forces tear at the fabric of space far away, we live near a far smaller star whose own activity carries risks of a different kind, risks not theoretical or remote, but inevitable on human timescales. Solar storms waiting for the next strike. In 1859, the Earth was struck by an event now remembered as the Carrington event. A massive coronal mass ejection erupted from the Sun and hurled charged particles directly at our planet. Within hours, auroras blazed across the globe, glowing even near the tropics. Telegraph systems sparked and caught fire. Wires melted, equipment failed, and operators received electric shocks. At that time, the damage was disruptive but not catastrophic. Life went on, because society was not yet dependent on global electricity or satellite networks. But if the same scale event occurred today, the outcome would be far more severe. Modern civilization relies on electrical grids, satellites, navigation systems, and fragile electronics embedded into nearly every aspect of daily life. A Carrington-scale solar storm in our era could cripple satellites, destroy power infrastructure, and overwhelm communication systems worldwide. The surges induced into grids could trigger cascading failures, leading to blackouts that last not for hours or days, but for months or even years before full recovery. Air traffic would be forced to halt. GPS would be unreliable if not offline entirely. Financial systems would freeze, and the internet could fail across countries at once. In a matter of hours, the technological framework that society assumes to be permanent could fracture on a global scale. This is not an unlikely scenario. The Sun constantly hurls eruptions outward. Most are small enough to be deflected or absorbed by Earth's magnetic field, but some exceed that protection. Observations made of Sun-like stars beyond our system show that violent coronal mass ejections are not rare in the cosmos. Some stars, not profoundly different from our own, have unleashed eruptions powerful enough to strip atmospheres from nearby planets. That evidence makes clear that the risk for our world is not hypothetical. The question is not whether, but when. Preparedness rests on vigilance. Monitoring stations like the Solar Dynamics Observatory track the sun's surface daily, while space weather forecasting agencies issue alerts when eruptions are detected. With hours of warning, satellites can be put into safe modes and sections of power grids can be deliberately powered down to reduce damage. Yet these defenses only soften the blow. They cannot prevent it. A superstorm cannot be deflected or neutralized. It can only be endured. The limitation is sobering. Unlike threats we might one day redirect or destroy, a solar superstorm reminds us that survival often depends on endurance rather than resistance. And endurance holds weight in another direction as well, because when people speak of pushing beyond Earth and venturing toward the stars, endurance is the very thing the numbers do not allow. The futility of interstellar travel. For as long as people have looked into the night sky, the idea of reaching the stars has seemed inevitable. Science fiction imagines it as only a matter of technology, ships leaving Earth, new planets colonized, humanity expanding outward. The dream feels within reach when we picture steady progress. Yet the scale of interstellar space imposes limits that engineering alone cannot erase, and those limits are sobering. Voyager 1 offers a clear example. Launched in 1977, it is the most distant probe ever built, still racing away at extraordinary speed after decades. Even so, its velocity underlines the barrier we face. To cover the gulf to the nearest star system would take such a probe tens of thousands of years. That single journey would exceed the span of recorded history many times over. What science fiction imagines as a voyage is, in reality, a timeline so extreme it makes human participation nearly impossible. The challenges for crewed missions are even more daunting. 3 obstacles stand out above all others. First, life support. Sustaining human beings across centuries requires steady food, water, and closed systems that never fail. Second, radiation. Interstellar space is filled with high-energy particles that would steadily damage both crew and ship, demanding levels of shielding we cannot yet provide. Third, propulsion energy. Accelerating a vessel carrying people to even a fraction of light speed is beyond any technology we possess, requiring power sources orders of magnitude greater than our rockets. Each one of these difficulties is formidable on its own. Together, they press the concept of human interstellar travel into impossibility. Ambitious ideas exist. Proposals like nuclear propulsion aim to extend exploration within our solar system, yet even they would cut only a fragment off the times required for nearby stars. Projects such as Breakthrough Starshot aim to use lasers to propel tiny, lightweight probes between stars, but their payloads would be gram-sized sensors, not people. At best, such missions would send postcards across the void, not colonists. Taken together, these realities mean that interstellar travel, rather than a path forward, may remain a boundary. Human beings might see distant suns only through telescopes, their warmth and light forever unreachable in practice. And in the rare thought experiments where a ship does set out, another barrier forces itself into view, not distance alone, but time itself, stretching in ways that separate travelers from the people they leave behind. Forever separated by relativity. Imagine a future where a crew departs on a successful interstellar voyage. Advanced propulsion pushes their ship close to a significant fraction of light speed, and for those on board, the clocks run in what feels like normal time, days, months, and years passing as expected. Yet hidden in this achievement lies a consequence built into the fabric of the universe. Special relativity ensures that life on Earth does not unfold at the same pace. The principle is called time dilation. As velocity increases toward the speed of light, time for the travelers slows down compared to those watching from home. To the crew, the trip may last only decades and birthdays arrive in regular rhythm. But for those left on Earth, far more time will have elapsed, centuries or even millennia, depending on the speed and distance covered. The relativity gap does not erase family or home, but it makes practical reunion impossible. The two groups age along different timelines, permanently out of sync with one another. One simple example makes this clear. A journey to a star system just 10 light-years away, if taken at a tenth of light speed, would appear to last about a century when measured from Earth. Yet because of time dilation, the people who leave onboard might feel as though only a few decades passed. When they arrive, the Earth they knew would already be in the deep future. Their original society would have changed beyond recognition, generations replaced by descendants the travelers could never know. Home continues forward, while the Voyagers remain anchored to a slower clock. This outcome is not a paradox but a consequence of physics that all observers agree on. From Earth's point of view, the ship's clocks have lagged behind. From the ship's point of view, Earth has aged rapidly. Both are correct, and neither can be reconciled in a way that restores the bond between them. Time dilation ensures that any journey near light speed is also a permanent break, creating not just distance but an irreversible fracture in shared history. In that sense, interstellar travel would not only move people away in space, but also lock them into an unbridgeable separation in time. And while that thought emphasizes how travelers lose their connection to Earth, there is another reminder much closer at hand of how separation defines existence, something that applies not just to journeys between stars, but to every step we take here at home. Earth never returns to the same spot. Earth is always in motion, carried through space on paths we rarely think about. It spins once every 24 hours, orbits the sun once every year, and rides along with the solar system as the sun moves around the center of the Milky Way. On larger scales, even the Milky Way itself is in motion relative to other galaxies and to the cosmic microwave background. Because of these overlapping motions, the planet never occupies the exact same cosmic coordinates twice. This means that even in the short span of a few minutes, Earth has already shifted thousands of miles from where it was before. The orbit we picture as a neat loop around the sun is actually a spiral when factored into the sun's galactic orbit, a line that never closes on itself. From the ground it feels simple, but in 3 dimensions the reality is constant displacement. The point in space where Earth was yesterday is gone forever, and no orbital cycle will take it back. The solar system as a whole contributes to this unending drift. As the planets circle the sun itself travels at hundreds of thousands of miles per hour around the galactic center, carrying everything within its gravity well along with it. This galactic journey takes about 225 million years to complete, so since Earth first formed, the solar system has made only a few dozen orbits of the galaxy. In that time, every position our planet has passed through has been abandoned permanently, each new second marking another step away from all that came before. The expansion of the universe adds yet another layer, pushing galaxies farther and farther apart. If we tried to define a fixed position in the cosmos, the steady stretching of space would undo it instantly. What we think of as location is never stable, always moving on scales far larger than human reference points. The ground beneath us may feel steady, but in reality it is part of a path that never repeats. Understanding this motion shifts perspective. No two instants in Earth's history occupy the same point in the universe, making every moment a unique arrangement of time and space. That sense of transience emphasizes how temporary our place is. And just beyond our moving world, another challenge unfolds, not in cosmic distances, but in the crowded trail humanity has left around its own planet. Space debris, invisible bullets. Just above Earth's atmosphere lies a zone that looks quiet from the ground but is anything but empty. Low Earth orbit has become crowded with fragments of past missions, broken satellites, rocket parts, and even flecks of paint left behind decades ago. Each piece moves at thousands of kilometers per hour, and at those velocities even millimeter-sized debris carries destructive energy. A shard that's small can puncture metal panels, crack a window, or breach protective layers, turning routine orbit into hazardous territory. For astronauts conducting spacewalks, this is a constant danger. Large objects can be tracked and avoided, but many smaller fragments slip beneath detection. A paint chip moving faster than a bullet cannot be seen in time to react, and a direct strike on a spacesuit would leave virtually no chance for survival. Spacesuit design incorporates layered shielding to resist these threats, but protections only work up to a point. Beyond certain speeds, even the best materials offer little defense. Satellites face similar risks. Every operational spacecraft must account for collisions with fragments large enough to track, forcing routine course adjustments that burn fuel and shorten mission lifetimes. For smaller debris, avoidance is impossible. One random impact at orbital speeds can render a satellite useless. Worse still, the collision produces fresh clouds of fragments that spread the hazard even further, increasing the danger for everything still circling Earth. This feedback loop is known as a cascading effect, where one impact multiplies the threat and accelerates the problem. Space agencies maintain constant watch over orbital space, tracking tens of thousands of larger objects and issuing alerts when risks are detected. Collision avoidance maneuvers are now standard procedure, built into the operations of nearly every satellite. But tracking alone cannot solve the problem. Without mitigation, low Earth orbit could eventually resemble a debris field dense enough to make new launches unsafe. To counter this, initiatives like the European Space Agency's Clear Space mission are testing ways to remove fragments, demonstrating that active cleanup will be necessary for long-term sustainability. The situation above Earth illustrates a broader truth. The universe is not hostile only because of vast distances or extreme events, but also because even our own near-space environment can become a place of unseen hazards. And if that reality feels difficult to process, it mirrors something larger. Because once we look beyond immediate dangers, the very idea of the universe itself leads us into questions that strain the limits of human comprehension. The absurdity of infinity. Infinity is one of those concepts that feels impossible to hold in the mind. If the universe has no boundary, then it extends endlessly in all directions, with no final surface to reach and no horizon to close it off. That alone defies experience, because everything we know, rooms, bodies, planets, has edges we can point to and measure. An infinite cosmos rejects that logic outright, offering no limit we can picture and no conclusion we can reach. But the opposite scenario feels no easier. If the universe is finite, then in some direction there must be an end. That might sound more manageable at first until the next question arrives. What exists beyond it? If there is a boundary, then the universe would sit inside something else, an outside larger than all of space and time. By definition, that makes no sense, yet a finite cosmos cannot avoid it. In both versions, infinity or a limit, language fails and intuition breaks down. Cosmologists admit this openly. Observations refine shapes, geometries, and expansion rates, but no amount of data settles the core question. Is it endless or bounded? Infinity itself resists definition, and finitude creates contradictions. Each possibility pushes human reasoning into places it cannot resolve. That is why the idea of infinity is not just abstract. Its very suggestion leaves us facing the outer wall of our own comprehension. The paradox is simple to state but impossible to solve. An infinite universe cannot be pictured, and a finite one forces us to ask what sits outside of everything. Both dismantle the tools people usually use to make sense of the world. In the end, cosmology leaves no choice but to live with both possibilities unresolved, because neither offers comfort or closure. Either way, the scale of the question highlights why people chase these puzzles. The more answers we find, the more limits of knowledge are revealed. Infinity, whether real or not, keeps existence unsettled. And beyond questions of size and shape lies something just as unnerving, not abstract mysteries of boundaries, but the reality that destruction in this universe can arrive instantly, giving no warning at all. Instant annihilation events. There are certain cosmic events so fast and decisive that survival is not part of the outcome. Gamma-ray bursts belong to this category. Triggered when massive stars collapse or when neutron stars collide, they unleash beams of energy so concentrated that, if aimed in our direction, the results would be devastating. Earth's atmosphere would erode, radiation would flood the surface, and extinction would follow before anyone had time to perceive danger. These events are scientifically possible, but astronomers stress that such alignments are extraordinarily rare, and the odds of one striking this planet are vanishingly small. Even more unsettling in concept is something called vacuum decay. This scenario does not come from observation but from theoretical physics. If the vacuum state that supports all quantum fields is only metastable, then one day it could collapse to a lower energy state. If that happened, the change would ripple outward at the speed of light, rewriting the very rules of matter and energy as it moved. Molecules, stars, and planets alike would be undone in an instant. No transition, no signal, no warning, only immediate reconfiguration into a universe defined by unfamiliar physics. Importantly, physicists emphasize this remains speculative. There is no evidence our vacuum is unstable, and it lives more in the realm of mathematical possibility than in any forecast of things to come. What unites these ideas is not their likelihood, but their demonstration of how fragile assumptions about permanence can be. Gamma-ray bursts happen in reality, though rarely, while vacuum decay is little more than a logical edge case in theory. In both, the emphasis is not on predictions of imminent catastrophe, but on the reminder that the rules guiding existence include processes that, if they occurred nearby, would unfold too quickly for response. They belong to the category of events a species cannot prepare against, because by the time one arrives, its conclusion already exists. This contrast between ordinary dangers we can see building and events too sudden to resist illustrates the spectrum of threats woven into the universe. Some strike without warning, arriving out of nowhere. Others wander slowly, looming in distances we cannot easily measure, always out there but capable of appearing close when least expected. Rogue planets, intruders in the dark. Some cosmic threats are not bursts of energy or collapsing stars, but planets without suns, rogue planets drifting unnoticed through the dark. Unlike Earth and its neighbors, which orbit securely around a star, these worlds travel alone, ejected from their home systems or forming independently in the cold void. With no starlight to reveal them, they are almost invisible, detectable only when their gravity bends the light of distant stars in brief flashes we call microlensing. The danger these interstellar wanderers pose comes not from collisions, but from the pull of gravity during a close passage. A massive rogue planet passing near our solar system could disturb the balance of planetary orbits. Even a small deviation might tilt Earth's path around the Sun enough to destabilize climate cycles or disrupt seasonal rhythms. At higher masses, the outcomes are more severe. Possible ejection of planets from their orbits, altered arrangements in the asteroid belt, or chain reactions leading to long-term instability across the solar system. The scenario is exceedingly unlikely, but its potential consequences make it one of the most dramatic gravitational risks imaginable. Simulations show that even bodies smaller than Jupiter could create ripple effects felt for thousands of years. A shift to the asteroid belt, for example, could scatter debris inward, raising the chance of impacts on Earth. Cascading disturbances like these would extend far beyond a single close pass, with instability continuing to shape planetary dynamics long after the rogue planet moved on. The solar system's apparent order thus conceals a fragility, its harmony vulnerable to an unseen object with the right mass and timing. Because they emit no light of their own, rogue planets are difficult to detect, but this is slowly changing. ESA's Gaia mission already refines stellar positions precisely enough to reveal gravitational anomalies that betray drifting planets. The upcoming Nancy Grace Roman Space Telescope is expected to expand this effort, using microlensing surveys to uncover thousands of new exoplanets, including free-floating worlds. Each discovery adds to the understanding that rogue planets are not rare accidents, but common results of star system evolution. Astronomers now recognize our galaxy is home not only to stable planetary systems like our own, but also to these silent wanderers, objects that drift for billions of years, waiting to intersect with the settled structures of stars and worlds. And while some regions of the universe are crowded with hidden threats like these, others are marked by the opposite: vast stretches of space where almost nothing exists at all. The Boots Void, a cosmic desert. The Boots Void, sometimes called the Great Void, stands out as one of the most mysterious structures astronomers have ever charted. Spanning hundreds of millions of light-years across, it is among the largest known voids in the observable universe. To frame that scale, an expanse this wide could easily contain tens of thousands of galaxies if matter were spread in its average distribution. Yet when scientists mapped the region, almost nothing appeared. Instead of the dense cosmic web expected, the Boots Void revealed itself as a cosmic desert, drastically underfilled with galaxies where abundance should have been. Under ordinary conditions, such a volume of space ought to host a vibrant population of galaxies, clusters and filaments woven together into the great cosmic web. Instead, the Boots Void contains only about 60. Compared against the tens of thousands presumed in more typical areas, the contrast is stark. This mismatch remains one of the most striking large-scale structure puzzles in cosmology, a reminder that while our models describe broad patterns, they do not yet account for why certain regions are left nearly empty. Explanations remain tentative. Some researchers think the Boots Void grew through the gradual merging of smaller voids over billions of years, leaving behind a region of exceptional emptiness. Others point to the role of dark matter, suggesting that this expanse may lie in an unusually low-density patch, where gravitational attraction was too weak to seed galaxy formation. These ideas are consistent with what simulations of large-scale structure show, but none fully capture why the gap is so extreme compared to predictions. The alternative is that something about how dark matter or dark energy shapes the cosmos operates differently inside voids, and the Boots Void may be one of the best natural laboratories for testing those possibilities. Because voids can also leave subtle signatures on the cosmic microwave background and the distribution of galaxies near their rims, they are now carefully studied as tools to probe the behavior of dark matter and dark energy. The Boots Void remains a reminder that cosmic structure is not uniform, but laced with deserts as well as islands of light. Its sheer emptiness unsettles, because it signals that even the average patterns we rely on are not reliable everywhere. And if such vast regions can exist with almost nothing inside them, other cosmic entities reveal their presence in the exact opposite way, by moving unpredictably, carrying their immense gravity with them into places that, until suddenly, seemed secure. Wandering black holes. Black holes are already among the strangest objects in the universe, but the idea that some wander freely without being bound to any star system adds another level of unease. These rogue black holes drift unseen through galaxies, carrying immense gravity yet giving off no light. Unlike the supermassive black holes fixed in galactic centers, the unanchored kind travel independently, detectable only through the effects they leave on the matter around them. They remain hidden until their gravity reveals them by altering the behavior of nearby stars or gas. The Gaia telescope has become a powerful tool in this search. By charting the positions and subtle shifts in the movements of stars with remarkable accuracy, Gaia gives astronomers a way to notice disturbances caused by invisible objects. If a star seems to wobble or accelerate in an unexpected way, it may be under the influence of a black hole. Alongside Gaia, pulsar timing has also become an important detection method. Pulsars send out radio pulses with extraordinary regularity, and any slight distortions in their timing can signal the presence of massive objects tugging on them. Recent studies using these techniques have even suggested the existence of dark matter clumps or wandering compact objects close enough to produce measurable gravitational effects, quiet evidence of masses we cannot see. The reason these wanderers matter is because of how little warning they would give if one passed nearby. A rogue black hole does not shine, and unless it is actively feeding on matter, it is nearly invisible to conventional telescopes. If one were to drift into the outer reaches of our solar system, the encounter would not be visible as a catastrophic collision, but as subtle distortions in orbital paths. Over time, planets could be nudged out of their stable rhythms, climates could destabilize, and smaller bodies like asteroids could be stirred onto dangerous new trajectories. The probability of this happening close to Earth is very low, but the scale of disruption a single compact object could cause shows how fragile planetary order can be. Unlike asteroids, which can be tracked and possibly diverted, there is no way to deflect or resist an object with the mass of a black hole. Detection and monitoring remain the only defenses, and even then uncertainty dominates. These searches underscore how much of the universe remains hidden from straightforward observation, reminding us that some of the greatest risks come not from what can be seen, but from what bends reality in silence. And yet, beyond even these stealth objects, lies a question more unsettling. The fact that we still cannot explain what the universe itself is made of, or how it began at all. The unknown origin of everything. For all the progress made in astronomy, the most basic questions remain unanswered. We know the universe's mass, energy budget is dominated by dark energy and dark matter, but their true nature is still unknown. Ordinary matter, the stars, planets, and galaxies we can see, accounts for less than 5% of the total. Dark matter acts as invisible scaffolding, holding galaxies together with gravity we cannot directly detect, while dark energy drives the overall expansion of space itself. In 2025, data from the Dark Energy Spectroscopic Instrument began strengthening hints that dark energy might actually evolve over time. If that is true, it would challenge one of the central assumptions of physics and reshape every model of the cosmos. Even with advances from missions like the James Webb Space Telescope, the biggest mysteries remain out of reach. JWST now provides our sharpest views of galaxies that formed just a few 100 million years after the universe began. Yet none of those images tell us what dark matter is, or why dark energy behaves the way it does. Even the rate of cosmic expansion is unsettled. Conflicting measurements of the Hubble constant leave no clear answer about how fast the universe grows. This unresolved Hubble tension throws uncertainty onto questions of both origin and fate. Each new set of data clarifies details but complicates the big picture. We know more about the universe's ingredients than ever before, but not what they fundamentally are. When cosmologists turn to the Big Bang itself, the limits of our theories appear starkest. The model explains how the universe expanded from an unimaginably hot and dense beginning, but it cannot say what produced those starting conditions or why they existed at all. Some researchers explore speculative frameworks, such as mirror universes or quantum phenomena seeding the earliest moments of space and time. These models remain unproven, but they highlight the possibility that our current physics may never fully capture the universe's first cause. The unknown origin of everything signals that we may not have access to a complete explanation, even with perfect instruments. That uncertainty is what makes present-day missions critical. JWST DAISY and the upcoming Roman Space Telescope do not promise final answers, but they narrow the mystery step by step. Every galaxy mapped, every spectrum analyzed, and every signal compared brings us closer to defining the question itself more clearly. In the end, what unsettles most is how incomplete our knowledge still is. And it is this gap, between what we can measure and what we cannot, that frames the larger truth about our place in the cosmos. Taken together, these 24 facts reveal how limited and fragile humanity is against the scale of the universe. Invisible forces still dictate how galaxies hold together, and sudden events could erase what we build without warning. Our species has little control over the cosmic environment that surrounds us. Yet science is pushing back against that uncertainty. DAISY, JWST, the Vera Rubin Observatory, and planetary defense missions all represent efforts to study what threatens us and what keeps us alive. Exploration marks both our vulnerability and our resilience. If you want clear, research-backed updates on these cosmic risks and discoveries, subscribe and hit the bell.